So we'll continue. So this is the load flow analysis. You can also see the representation in the tabular form. Network 1, if you find out the theoretical values by the Gauss-Seidel method, the adaptive Newton-Raphson method is used in the simulation. If you find it by theoretical, the output is for network 1 12.6 and the simulation result observed is 12.1 in network 1. If I speak about network 3, theoretical result shows 14.7, whereas simulation result is almost 14 megawatt. So you can have a comparative analysis for theoretical as well as simulation results. Now you can also find out the power output at various wind speeds. The power generated from wind turbine normally depends upon the wind speed in meter per second. It is well known that the power generated is directly proportional to the wind speed in meter per second. The cut-in speed of the wind turbine generator, in this case being 4 meter per second, a simulation study was carried in the generic model where the active power for wind speed of 4 meter per second to 14 meter per second was simulated. This can also be expressed in the formula given below, in the sense P wind is equal to half rho A pi r square V to the power 3, where the rho stands for the air density, r the radius, and v the velocity of wind or the wind speed. Well, simulation result for individual wind speed yields you the result. You can also see that as the wind speed increases, the power output is normally going to increase. So this is the tabular representation of the simulation results which were performed at various wind speeds. This is the power curve which you obtain when you plot the readings with respect to the power output in megawatt and the wind speed in meter per second. One more analysis which you can perform in the software is the short circuit analysis. Now, short circuit analysis is very important when you decide the rating of the protective devices. You want to make your system ready for an abnormal condition and recover from it. So short circuit analysis is generally done to decide the impact of individual fault on the system with the recovery time and ratings of the protective devices to be implemented. Now you can perform two faults in the system, analyze two faults in the system. The first one is a single line to ground fault and the second one is three-phase short circuit fault. As we know that single line to ground fault is an unsymmetrical fault and the three-phase short circuit fault is a symmetrical fault in which the currents are going to be the same. So when we perform a single line fault on bus 1, single line to ground fault on bus 1, you can observe that the rated voltage at bus 1 is 132 kV. At bus 1 it is 132 kV. A fault was introduced at almost 3 seconds. When the fault was introduced at 3 seconds, you can observe that because it's a single line to ground fault, the voltage, it's the bus voltage dropped to almost 70% of the rated voltage, and it took almost less than 0.5 seconds to recover. And when it recovered, there was still some oscillations. There were some oscillations in the system, and it did not recover 100%. When you really use it on the software, you can zoom it and you can find the values at every instant. So this is the graph for the impact of single line to ground fault on bus 1. This is the tabular form of the rated voltage. You can observe that although the fault was cleared at 3.5 seconds, but it actually came up to its rated voltage of 132 kilovolt at 4.44 seconds. So this gives an idea to a power system engineer to make use of proper protective devices, and it also gives you an idea of recovery system. Now this is the second fault which we performed in the software, that is three-phase short circuit fault. And we all know that three-phase short circuit fault is much more severe as compared to the single line to ground fault. Here in three-phase short circuit fault, the voltage drop almost to 0%. You can observe that the system was operating at voltage of 132 kilovolt, but as the fault was introduced at almost 3 seconds, the x-axis represents the time, the voltage dropped almost to 0 volts, and it recovered at less than 4 seconds. And although it shows the same characteristics which was observed in single line to ground fault, that there are certain oscillations in the system, and for it to occupy steady state condition, it did require some time. So this can also be represented in the tabular form. Although the fault was cleared at 3.5 seconds, the system voltage was 123 kilovolt, whereas it took almost 4.441 second to attain its rated voltage of 132 kilovolt. So during the presence of the fault, the voltage dipped down to almost 0 kilovolt. After the fault clearing at 3.5 seconds, the system started recovering, and it was found that the normal operating conditions were attained after 0.94 seconds. So this is the comparison. You can observe that in the single line to ground fault, the voltage dropped to almost 86 kilovolt. In case of a three-phase fault, it dropped to almost 0 kilovolt. The recovery time in single line to ground fault was much less, that it took 0.5 seconds, whereas in case of three-phase fault, it took it took more time. It took 0.94 seconds as compared to the single line to ground fault. So this is one more analysis which you can do in the software in terms of power quality. The second analysis, a very important analysis from the power quality point of view, is the harmonic analysis. Now the wind farm should maintain the quality of power being delivered to the grid. Harmonics in the system are the primary cause of use of electronic devices, along with frequent switching and variable nature of wind speed. The harmonic analysis was performed on the wind farm, and the priority was given to the analysis at bus 1, which is 132 kilovolt. The harmonic content in terms of percentage THD, if violates the grid codes, then there was a need to design and implement a specific harmonic filter. Now how we did it, we'll just discuss it here. This is the overview of the wind farm. You can observe that when I simulate it for harmonic case study, you can observe that the harmonic content at a bus of 33 kV was almost 18.59%, but as it approached a higher bus level of 132 kilovolt, although the harmonic content decreased, but it is 3.61. As per the grid codes, the THD at bus of 132 kilovolt should be less than 3%. So to improve the power quality and considering the grid codes, it was important to design a harmonic filter. So in this case, we can also observe the harmonic THD, percentage THD at different locations in the network. Now this is for network 1. You can see the percentage THD is more at the WTG, nearer to the WTG. This is the harmonic waveform. You can observe that bus 1, which is 132 kilovolt, it is showing percentage of 3% THD. So it is not purely sinusoidal rather, but it's pretty more sinusoidal as compared to bus 2 and bus 6 of 33 kilovolt. This is the harmonic spectrum for bus 1, bus 2 and bus 6. You can observe that for bus 1 the harmonic order is less as compared to bus 2 and bus 3, and you can also observe that the fifth order harmonic is dominant in the system. This is the fifth order harmonic which is dominant in the system. This is the comparative table of harmonic content at various locations. At the wind turbine generator, it is percentage THD is 18%, whereas at bus 1 it is almost 3.6%, but it is still violating the grid codes. So what is important is if it is violating the grid codes, you have to design a specific harmonic filter. Now what are the calculations involved in designing a harmonic filter? The existing power factor is 0.85, so you can find out tan phi. The kVR required, the formula for kVR required is given here. You have to substitute the values the capacity in terms of kW is 40,000. I substituted and I'll have to find the value of capacitance. Now for Xc is equal to 50, Xc is equal to 1 by 2 pi Fc. Substituting, you will be getting the value of the inductive capacitance. Now we know that the fifth order harmonic is dominant in the system. Now I have to design the filter for fifth order. So Xc will be now 250 because the fundamental frequency was 50 Hertz. So from that you can find out Xc at 250. Also you will be able to find XL at 250. You have to substitute these values in the harmonic filter which is implemented here. You have to implement design and implement the harmonic filter, and you can observe that once a proper harmonic filter is being implemented, you can observe at bus 1, which was of prime concern, the percentage TSD before implementation of the harmonic filter was 3.61% approximately. Now it has lowered to 1.07%. So this is an indication of proper implementation of a harmonic filter in the system. You can observe that after the implementation of the harmonic filter, then harmonic analysis at network 1. You can also observe that at various buses now, as compared to the previous harmonic waveform without filter, this waveform is pretty more sinusoidal, so it's an indication of a good power quality. You can also observe that the spectrum, the range of the spectrum has also reduced. Although it is the fifth order harmonic is dominant in the system, you can observe that this is raising almost to 1.7, whereas in case of without harmonic filter it raised almost till 8. So again, this is an indication of proper implementation of the harmonic filter. So calculating it properly and designing and implementing it is very important. Also, implementation of harmonic filter location is also very important. Various factors have to be considered, like what is the operating voltage, because more the operating voltage, again there are certain economic aspects which are going to be coming into consideration. So implementation of the harmonic filter is yet another concern to a power system engineer. So this is the tabular representation without and with filter at bus 1. The percentage TSD without harmonic filter is 3.6, whereas with filter it has reduced to 1.07%. So it is as per the grade codes. One more analysis which you can perform in the software is reactive power analysis. We all know that reactive power compensation is very important for optimum and efficient operation of your power system. So as we know that the wind farm was giving a power output of 40 megawatt, but we did not analyze it for reactive power, like how much reactive power it was drawing. So you can observe that it is almost 28.5 MVAR, and it's pretty high. So what are the possible measures you can implement for reactive power compensation? So to begin with, the most simplest of all is to design and implement a capacitor bank, right? So you can also see that for network 1 and network 2 it is specifically taking minus 17 MVAR, and for network 3 individually it is taking 9.19 MVAR. So design and implementation of a capacitor bank is important in this aspect. So these are the calculations which you have to go through for designing a capacitor bank. So once a capacitor bank is being designed and implemented, you can observe that you can also compensate for a proper reactive power, and we can also see that there is a increase in power output. Reactive power analysis is also very important when it comes to your power system. So these are some of the modules which you can perform in the software. So the design and implementation of the capacitor bank was fruitful in reducing the reactive power demand, but previously the wind farm was taking reactive power 28.5 MVA. After the use of capacitor bank, it was consuming merely 1.93. So the cost of capacitor bank and design is again a matter of economics, but a long-term perspective with respect to voltage stability is important. So that's it from now. Thank you.